Hello, everyone, whether you are here with us at Hainan University or joining online, welcome to today's special academic lecture. I'm Yijin Long from Hainan University and the School of Physics and Optoelectronic Engineering. And our school is going through some exciting changes, especially since Hainan province was named a free trade province. This means that we are focusing more on creating an inclusive academic environment by inviting top scholars like Professor Junye from all around the world to share their knowledge. So today, it's our great pleasure and great honor to have Professor Junye sharing with us his recent very exciting works like a nuclear clocks. This is very exciting topic. He's a world famous experimentalist in quantum science and quantum metrology, particularly in advancing atomic clocks and fundamental physics. His research is helping us understanding quantum phenomena better, like controlling how atoms interact, studying how gravity affects time, and using spin entanglement for comparing clocks. Professor Junye has received many awards and honors for his great works, including the 2022 gold medal for optical atomic clock and the breakthrough prize in physics and the same year. And with roles and the NIST and the University of Colorado and Boulder, he brings a wealth of experience to today's lecture with the title The Quantum Frontier for Atomic Clocks and Fundamental Physics. Let's give a warm welcome to Professor Junye as we dive into this fascinating topic together. So let's welcome.
谢谢。我来 share 一下。So let me see if I can find the annotation.
Yes, it works now.
It works.
Perfect. Yeah.
Okay, perfect.
And let's see. Making sure that animation also works. Is that working?
Yes. Looks very good. Yeah.
Very good. Okay, thank you very much. Sorry about that.
Thanks for this. Yeah.
So as I said, thank you for the invitation, and I hope you will enjoy next 40 minutes, 15 minutes of the scientific discussions. If there's a question, I cannot see the screen, but maybe Carl, you can tell me if there are people asking questions, you can just stop me. I would rather interact with students and so on if there are questions. Okay, but otherwise I'll get started now.
Yes, go ahead.
So I want to start with talking about atomic clocks. And we have all learned in the first year quantum mechanics, the reason why we build quantum atomic clocks is because of Niels Bohr had this Bohr model that tells you that electrons moving around nucleus, and you have a prescribed orbitals, and the energies between these electronic orbitals is fixed. This is a quantization of the electronic orbitals around nucleus. And that's really the basis of quantum mechanics. In some sense, is very interesting. On one hand, gives you the absolute certainty that your energy spacing between these two electronic levels does not depend on who makes the measurement. It's the fundamental laws of nature. And that's why we want to use this as our standard, because anybody can do this measurement. As long as your measurement is done right, you should give the same answer regardless of where you are. So you can use these to explore fundamental physics. On the other hand, quantum physics also gives us uncertainty. Everybody has heard about Heisenberg's uncertainty principle. And the uncertainty principle concerns the fact that if you have a Hamiltonian and you write down the eigenstates of your system, and those states are so-called produce the good quantum numbers, and they have absolutely no uncertainty. The uncertainty comes in when you put the system into a so-called coherent superposition. And this coherent superposition could be a two-level system where the atom can be in the ground state or the excited state, such as ground state, excited state. And when you put it in coherent superposition, you can see because there is the energy difference E between the excited state and the ground state, if you wait a certain time t, it will develop a phase shift, e to the IET. This phase shift you can think of as if a fictitious spin half system, a spin half, spin up or down, can represent two-level system. So you can use a ball, looks like people call it block sphere. This block sphere can be used to represent Pauli matrices of spin half systems. You can spin down is the south pole, spin up is north pole. But when you put the system in coherent superposition between the ground state and excited state, you can think of this arrow is pointing to the equatorial plane. This arrow is not stationary. It's going to move around because there's this phase shift. What we build atomic clock for is to measure this phase shift extremely precisely by creating the superposition of between the ground state and excited state. But when you try to measure whether the atom is in the ground state or excited state, there's intrinsic uncertainty. You don't know. And that's the key problem, I would say key feature of quantum mechanics is you don't have a priori information about what state you are in when you're in coherent superposition. And that gives rise to the quantum noise because of this uncertainty principle. Another way of thinking about it is like a commutation relationship. Jx, Jy produce Jz, and they are non-commutable. And Jx, Jy are angular momentum operators to describe like Pauli matrices of the level 2 spin half system. When I say spin here, it's a pseudo spin. Up and down represents ground state and excited state. So that's the very, very basic principle of quantum mechanics. It has the two really most interesting features of quantum physics, where on one hand, it gives rise to absolute framework where you can do the best precision measurements predicted by quantum mechanics. At the same time, introduce the only thing that's uncertain in this world is the quantum noise. And so it's seemingly contradictory, but it's actually what that features the quantum science. And I will tell you something about how we overcome these uncertainties, how we make the better measurements based on this certainty principles. It's really trying to survive between the uncertainty and uncertainty lies the entire interesting aspect of quantum science right now. So I wanted to, before I tell you about atomic clock, I want to give you a little bit of a time scale. Remember I told you that we can put the two states in coherent superposition. This coherent superposition is like electrons moving around the nucleus, oscillating back and forth. I don't know what this feature is being produced. It's not me. On the right-hand side, there's a balloon. Who put it here? Somebody is doing something to this. Okay, anyway, going back to this animation. This is the superposition of the ground excited state, and it's describing the electron cloud moving, oscillating back and forth around the nucleus. And usually the speed of this oscillation, or the period of this oscillation, is very short. And that's because electrons are moving extremely fast around nucleus on the time scale of a femtosecond. And so if I try to make a visual picture of a pendulum, and I slow this electron oscillation by a factor of 10 to the 15, 10 to the 10 and 1 to 15 zeros, then I can make this oscillation to be slowed down by 15 orders of magnitude and oscillating one cycle per second. And the reason why to give you the belabel this point is that if we look at the other side of a time scale, which is very macroscopic of the age of the entire universe, that's a 14 billion years, 10 to the 18 seconds. If you take a geometrical mean between this very microscopic time scale of electron moving around the nucleus and the macroscopic time scale of the age of the universe, the geometrical mean, the midpoint, turns out to be a minute. And so now, if I introduce a strontium atom to you, and we find two energy levels, ground state and metastable excited state, I can create a quantum superposition between those two states. and that quantum coherence can survive for 2 minutes. What does that mean? It means that if I use a pendulum like a strontium atom, it can oscillate at the speed of 1 femtosecond as a period, and it will keep oscillating for 2 minutes. This is equivalent as if you have made a pendulum like the old-fashioned this pendulum clock, and it's oscillating once per second, and has been oscillating since the beginning of the universe. The total number of oscillation would be the same. That's the point of the geometrical mean. And so it's really interesting that we can, in the modern science, we can design a system, get a strontium atom, prepare quantum coherence. This quantum coherence is so long, almost as if there's a 10 to the 17 cycles that's been going by, as if we have had a pendulum clock that's been oscillating over the entire age of the universe. And that's the reason we want to use this type of quantum coherence to build atomic clocks. As I promised, I will come back to talk about quantum noise. So the clock is trying to measure this phase evolution between the ground state and the excited state. That's e to the exponential minus ei et. This is the phase factor. The longer you wait, the more the phase it is. It's energy times t. The strontium coherence time is 120 seconds. So we can actually pick up a phase factors of, like I said, 10 to the 17 oscillation periods. That's a lot of phase factors you can accumulate. And therefore, you can make an extremely precise atomic clocks. And we typically use very stable, phase-stable lasers. I will talk about this towards the end of my lecture. But as I mentioned, each atom introduces noise because you don't know when you put atom in coherent superposition, you don't know in principle whether it's in the excited state or ground state when you try to make a measurement. And therefore, there's a so-called standard quantum limit where you don't make just one measurement, you make many, many measurements. The N, the capital N represents the number of measurements, or it could be representing the number of particles you have in the system. And the total noise scales as 1 over square root of the number of particles you have or number of measurements you have. And the whole game of quantum entanglement that's now underlying the revolution, the so-called second quantum revolution, is that when I have n particles, each one of them has independent noise in traditional quantum mechanics. But if these n particles can become correlated or become entangled, and in principle, each particle's noise can be hidden away by another particle. And in other way of saying, you have n particle, n atoms in the system, but when you measure it, there's only one copy of noise. And this copy of noise now becomes squeezed. Looks like it used to be looking like a sphere, now it becomes a little ellipse. And this is the so-called Heisenberg limit. You can see it's much, much better than the standard quantum limit, where it's a 1 over square root of n. It's not 1 over n. This correlation between quantum particles, where you can hide away this fundamental noise, the quantum noise between the particles, is a key feature of why quantum metrology, why quantum computing, why quantum communication, they're all relying on the same technology here. And so in some ways, it's actually very naive understanding of quantum correlation, how quantum correlation work. It's just because of their noise properties become identical between entangled particles. Okay, so I'm going to use that feature for atomic clock. And actually, I won't spend too much time talking about quantum correlations or entanglement, but I just want to tell you, this represents now a new frontier of quantum measurement. So the basic ingredients, if you think about where the frontiers of a quantum metrology lies, and how quantum measurement frontier and a precision measurement frontier will come together, is that you design for quantum systems that has tremendous quantum coherence time. And this Q is called a quality factor, dictating when you get a resonance, quantum resonance going, how long does it take to oscillate before it decays away? And this 10 to the 17, meaning this pendulum, this quantum pendulum will oscillate 10 to the 17 times before it decays away. And so it's got a very good quality factor. The second ingredient is to get as many quantum particles as possible in a system, because the standard quantum limit scales with square root of the particle numbers. The new frontier is to engineer quantum many-body states where these particles can, in principle, have entanglement. And therefore, you can actually achieve even better measurement precision by enhancing this optimization procedure and to scale the system measurement precision as a function of n instead of n to the power of half. To achieve these goals, over the past 20, 30, 40 years, the atomic physics, the community, quantum science community has been actually inventing lots of technologies. And many of these technologies come out of a basic science research. Quantum control has now given rise to very high quality factor optical transitions that I'm mentioning today. Laser technology, laser science has produced the stable lasers with optical coherence approaching a minute. Optical frequency comb allow you to synthesize electromagnetic fields in a phase coherent fashion. Quantum gas, making cold atoms and it produce quantum gas, allow you to engineer quantum many-body states. The field is moving extremely fast. These are the technology. I will tell you a little bit of each. Each one of them in the late 80s, late 90s, when I was a graduate student, early 2000s, I became a faculty member, and so on. Over the past 40 years, each one of those fundamental research at the beginning earned those practitioners Nobel Prizes in the field. But you can see throughout the talk, for making atomic clock to be better, like the slope showing here, the performance of the clock is a function of the time. The reason why it's moving away so fast, moving along so fast, is because of these fundamental research turns into technology very quickly, so that we can now, undergraduate students can make these ultra cold atoms, can engineer quantum many-body states, can talk about quantum entanglement and so on, and actually use it in the very best measurement device that we are designing and implementing. And that's really the spirit I want to share with you today. And the field is still moving along really fast. Optical atomic clock, for example, as of a few years ago, we reached measurement precision of few parts 10 to the minus 19, accuracy just above 10 to the 18. And 4 years later, we improved the precision by a factor of 50. Now, these are, in physics, it does not come very easy to improve, especially in precision measurement, to improve these factor of 2, a factor of 2s. But these are leaps and jumps of improvements of the measurement precision over the past 3 or 4 years, because of we learned better how to control these quantum systems, how to maximize quantum coherence, how to maximize the number of particles in the system, and eventually also to employ engineer and employ quantum entanglement. And you can see the even accuracy now is below 10 to the minus 18. So the whole lecture, if you don't get anything out of it, I think one thing you probably should remember is from this slide. Why are people so excited about quantum science? Why are everybody talking about quantum technology? Some of them are overselling it, for sure. There's certain parts of the hype is there, but there's some real substantial scientific gain that's been happening. And it really comes from two aspects. Quantum coherence, we tend to think about quantum physics describes something very microscopic. But the modern quantum technology, quantum science, is trying to expand the scale of quantum coherence. You can think of that when I say scale, both spatial scale as well as temporal scale, to try to make a quantum coherence as macroscopic as possible. So, there's a classical quantum boundary, as we say. Quantum physics is for something small. Classical physics is for something big. But that's exactly what we are trying to break that boundary. If you think about quantum computer, we are trying to make a quantum system that is actually large enough scale to preserve the quantum coherence and entanglement such that we can even use it to process information. And so I think the essence of the excitement of quantum science now is really just to expand the scale of quantum coherence, or you can think of expanding the scale of quantum wave function, really. So how do we do that? Well, there's external degrees of freedom. Particles in the thermal motion looks like that. They have, each one of them have velocities. But if you cool down the temperature, we all heard de Broglie wavelengths. Yes, the particles start to become like waves. If you cool the temperature further down, well, the de Broglie waves of individual particles start to overlap with their neighbors, and macroscopic quantum coherence will appear. This is the key. Suddenly, the external degrees of freedom has lots of entropy built in, but when you get to so-called quantum degeneracy, when the quantum wave functions overlap with each other, then you can have one macroscopic quantum states to describe a lot of particles. This is from external degrees of freedom. The internal degrees of freedom, suppose spins, in principle, they are all random from each other. But now we can create entangled states where, suppose I have 1,000 spins here, but I can make it such that when one spins up, all other spins are up. Or when one spin is down, every other spin is down. This is so-called a GHZ state. And you can immediately see, in this case, the noise has only one copy, even though you have n particles here, because there's only one up or one down. Instead of n copies of atoms, they all have up and downs in a random fashion. If we can control both external and internal degrees of freedom in engineering quantum coherence, engineering entanglement, then we have the entire quantum particles under control. We can use this to do communication, to do processing of information, to do precision measurement. And that's really the essence of a quantum revolution right now. So I would keep going on these both sides of the things, on the external degrees of freedom and also on the internal degrees of freedom. On the external degrees of freedom, for example, these three gentlemen won Nobel Prize in the late 90s. It's because of they invented the technique called laser cooling, where the atoms are very hot, moving around in room temperature, under room temperature. But when you can shine the laser beams from 3 orthogonal directions with a particularly tuned laser frequencies, you can actually so-called laser cooling. You can suck all the entropy out of this random samples of thermal atoms and cool them down within a few hundreds of a millisecond down to a fraction of microkelvin. And this is a really, really powerful technology because, your human beings are outside this little vacuum chamber. Inside this vacuum chamber with just a piece of glass, you have atoms sitting at hundreds of nanokelvin temperature, and it becomes macroscopic quantum mechanical because, people were soon after the laser cooling, these three gentlemen were able to demonstrate the so-called Bose-Einstein condensation, where the temperature is so low, the wave function of individual particles start to overlap with each other. And in this particular case, when these atoms are bosons, they all collapse down to the absolute ground state and forming a macroscopic quantum mechanical state of thousands of atoms occupying the same wave function. This is the wave function you can almost see with your naked eyes when you destroy it with a fluorescence light. And it's a very special state when every single particle is occupying the same external motional degrees of freedom.
May I ask a question?
Please.
These particles that's condensed at the bottom here that you showed, they have to be bosons, right?
That's correct.
But what happens when these particles are fermions?
That's an excellent question. That will take another hero. Her name is Deborah Jing.
Great.
Actually, she is my hero, and we used to work a lot together. But unfortunately, she passed away. So now that thank you for your question. So what she demonstrated, Debbie demonstrated was.
But that's what we call Fermi surface, right?
If those particles are fermions, they have to obey the so-called Fermi statistics, or Pauli exclusion principle, meaning if one particle is occupying one quantum state, other fermions, if they're identical, cannot occupy the same quantum state. And you have to line them up until you exhaust the number of particles. And the highest level is called Fermi energy. And this you can think of, it's a Fermi C. And now you can demonstrate these in your little vacuum chamber by cooling atoms down if those atoms are fermions. And in fact, when I build clocks, I use Debbie's fermions because fermions tend to be not wanting to interact with each other. Bosons want to interact with each other. They want to collapse on top of each other. Fermions want to stay away from each other. And that means if I want to build a system that does not have interaction, in principle, I want every particle to be identical. So I can avoid the frequency shift on the clocks. I want to use fermions. So around the year 2000, this is when I became a young professor. This was a dream, at the time. And so the key, thank you. And the key challenge is now you have lots of particles instead of one. How do you keep up with the quantum coherence? And that's the key challenge. Now you're dealing with lots of atoms now. Is it possible you still can keep that under control instead of one? And that came with the technology that was invented in the 1970s. This is the Arthur Ashkin working with Steve Chu back in the Bell Labs at the time. And Arthur Ashkin would later win Nobel Prize in 2019 for inventing the technique called optical tweezer. So unlike ions, which can be trapped because ions have charge and you have a Lorentz force, you can trap them. Neutral atoms do not have charge. And in order to trap neutral atoms, you have to create the so-called light shift, which is nothing but using laser beams to create spatially dependent AC stock shift. Looks like this little ball, but this little ball is made by a laser beam. And if you can use laser beam to deform the energy state of an atom, you can keep atom trapped in there. It's like if you have a little piece of paper on the ground. If you take up the comb, you comb your hair a little bit, get it charged up, you can pick up a piece of hair by using a comb because you can polarize the piece of paper using the electrical charge of your comb. And this is the same thing. Laser beam can polarize the atom and pick up the atom. And when you do that, usually the ground state and excited state, the spin down, spin up, those two states have a different deformation due to the laser beam. And that wouldn't be good because you're trying to measure energy difference between these two states for your clock. But when you trap them, the energy states are changed. And therefore your clock is no longer accurate. And then we came up with this new idea. This is actually Jeff Kimball was my postdoc advisor at Caltech in the late 90s. And Hidetoshi Katori at the University of Tokyo came up with these independent ideas of, well, what if we came up a wavelength where the deformation of the trapping potential for the excited state and the ground state is the same? If it's the same, then the motional degrees of freedom where the atom can move around inside the ball and the internal degrees of freedom where the atom can be ground state or excited state can then be separated because the two balls look exactly identical. This is actually key technology that has really enabled the advance of the optical atomic clocks using neutral atoms. But it sounds very simple. If you think about it, it's an extremely simple idea. And because of it's a simple idea that we can actually demonstrate it in the lab. You have the ground state, excited state. You have the external degrees of freedom is being confined in a trapping potential. And when atoms are cooled down to very low temperatures, their quantum states are formed inside the harmonic potential. You have quantized energy levels. These are external degrees of freedom, the so-called motional states. This is the internal degrees of freedom called spins or electronic states. And when we drive electronic states from ground state to the excited state, you're also driving the motional degrees of freedom at the same time, but you can pick a state where the motional degrees of freedom does not change, and that's what we call a carrier. You can see this carrier transition only cares about energy difference between the ground and excited state of the internal degrees of freedom, but has no external Doppler effect, no external motional degrees of freedom. The external degrees of freedom is actually carried out in the so-called blue sideband and the red sideband when you are changing the external degrees of freedom, the motional state by ±1. But because you have cooled atoms already to the absolute ground state, there is no, in principle, any population left. You can no longer drive them into a quantum state that's below zero. In quantum mechanics, there's no such state. Therefore, the red sideband is suppressed. And the reason why we haven't seen all the suppression here in this particular data is because there's still not fully cooled down to the ground zero. There's some population in this state. But these days, we can actually absolutely eliminate all of these populations. So I've told you all the ingredients in some sense of now how to build the clocks. You form a standing wave with a laser beam. If you send a laser beam and reflect it by mirror, you can form a standing wave. The standing wave at the antinodes, you can use this to polarize the atoms and trap them. It looks like, this, I'm expanding the central trap. Looks like a two-dimensional trap where dozens of atoms are trapped in there. And they can move around in the transverse directions. In the vertical direction is tightly trapped. And you can send the laser beams in the vertical direction and start to look at the spin degrees of freedom. When I say spin, you're just probing the electronic ground state to the excited state, putting them in coherent superposition, as I explained earlier, and make a measurement. And it turns out, as the measurement precision continued to improve, and I saw Shibo is also logged into this talk. Shibo is now professor at Beijing University. This was his paper when he was in my group as a postdoc. But you can put those atoms in coherent superposition, and you will say, I cannot build the best atomic clocks. But turns out, and that goes back to Daxun's question. Daxun's question was, if these were fermions, they're not supposed to interact. But if the precision is so good, even the fermions can interact, because the fermions just means that when you write the wave function for the two fermions, the overall wave function needs to be anti-symmetrized. That's what the Pauli's exclusion principle tells you. And I can do that by symmetrize the internal degrees of freedom and anti-symmetrize the external degrees of freedom. N1, N2 is sort of emotional degrees of freedom in this transverse plane. And then when they anti-symmetrize it, these atoms can still interact with each other. People call it P wave or E wave and so on. And so these are so-called odd partial waves. And odd partial waves means when you exchange the positions of two fermions, the wave function has a negative sign. That's where the Pauli exclusion principle tells you. And so we find out, well, that's a problem we need to solve. And so the latest work we did is by trapping atoms to extremely shallow lattice, so shallow that you can actually really see the gravitational potential energy difference between this level, and that level, that trapping side, this trapping side, that trapping side, they're separated by wavelengths divided by 2, because the reason why it's divided by 2, because it's a standing wave for the retroreflected laser beam. And as we learned in high school, when a stone is placed higher than above another stone, there's a gravitational potential energy difference. That's mgh. This is it's very much high school physics. It's just gravitational potential energy. Has nothing to do with relativity. But because the trapping potential is so shallow, the wave function of these particles are actually spread out among several different trapping sites. It's no longer confined as if, this atom is only confined in this pancake. In fact, when the trapping potential is so shallow, the wave function spreads out. The reason why I'm belaboring this point is that, well, because we're using the so-called magic wavelengths, the ground state, electronic state, and excited electronic state shares the exactly trapping potential. The wave function looks, when I drive the clock from ground state to the excited state, the wave function looks exactly the same. Now, because the atoms can occupy both this site and that site, these atoms do not look identical. These atoms on the same site look identical. So identical atoms interact through P wave because these are fermions. Non-identical fermions do not enjoy the protection of Pauli exclusion principle. Remember, Pauli exclusion principle only applies to indistinguishable particles. So if they're distinguishable fermions, you do not enjoy that Pauli exclusion principle. So you can have the so-called S-wave interaction. meaning that their wave function does not have to be anti-symmetrized. They can be symmetrized. And because I can engineer these different interactions, I can actually cancel out the frequency shift caused by atomic interactions for clocks. And I won't get into the details of this, but just want to give you the sense that when we see a problem in quantum physics, when you see a problem, when your measurement science tells you there's a problem, you can almost always find a way to engineer this away by just being a little smarter of how do you engineer quantum systems so that you can remove that effect from your measurement system. And so we can actually enjoy very long coherence time by driving the single frequency Rabi oscillations, or we can not only drive the same site, the atom from, I can drive the Rabi oscillations for atoms occupying from the same site, from the ground state to the excited state. I can also drive Rabi oscillation from atom which is in the ground state here, excited state up there. And this is what's shown by this arrow, meaning the atom wave function is now putting in a coherent superposition both in the ground state and excited state, as well as in site here and site there. It's a weird superposition. It's like I'm asking you to be, suppose I think of a human being to be an atom, and a superposition meaning yes, both head down or head up. And I ask you to be head up on the second floor, head down to be on the ground floor. And that's a superposition. You're living there like that. And we can measure these energy separations. Why this is interesting? Well, if you can put atoms in coherent superposition and then put atoms eventually to be spin up in the upstairs, spin down in the downstairs, if you waited for a little while, they will accumulate gravitational potential energy. So you can actually measure the phase shift caused by gravitational potential energy, meaning you can actually measure gravity. This is what people call the atom interferometer. This is the interferometry allow you to measure local gravity directly using quantum phase. At the same time, you can still measure your time because you're measuring the phase evolution between the excited state and the ground state. And that time has a connection to gravitational potential because of the Einstein's general relativity. So this clock, this interferometer cannot allow you to measure both local gravity as well as local gravity potential, gravitational potential at the same time. And I will tell you how we do the gravitational potential measurement. So here's actually the picture of atoms. We have these atoms confined in these individual standing wave antinodes. We can take a picture on the CCD camera, and we can look at the upper half of the atoms here versus atoms there. Yeah, every one of them is a clock. So you can think of there's one set of a pendulum upstairs, another set of a pendulum downstairs, and I can watch when I set them all go to the left and the pendulum start to swing back and forth, back and forth. You wait for a while. After 6 seconds, you can see every pendulum up there swinging to the left. The pendulum down here also swings to the left. This is why this is a diagonal. But you can start to see a little bit of a face start to show up. And if you wait for 30 seconds, it becomes ellipse. If you wait even longer, this opens up to be a circle, meaning these two sets of pendulums are swinging initially in phase, but eventually they move out of phase. Why would they move out of phase is because the frequency up here and the frequency down here is slightly different. Why would that be different? The clock is connected, and we can actually, this plot shows you that we can put these atoms in coherent superposition, and this coherence can be almost as long as 2 minutes. And this is amazing, right? These atoms can be put in coherent superposition, and you can go drink a cup of tea and come back. These atoms are still in coherent superposition. And the reason why the atoms up here and the atom down there measure different time is because Einstein's general relativity. We all know GPS, or in China, we have 北斗导航卫星. you have to use general relativity to tell you where you are. And for satellites, you have kilometers, hundreds of kilometers. You obviously have to take into general relativity into account. But for our experiment, the separation between the atoms here and up there is only a few hundred microns. A few hundred microns, we can still measure the time difference. That's because by Einstein's relativity theory, 1 meter difference will give rise to 10 to minus 16. So by the time you go to 100 micron, if you lift your clock by a width of a human hair, the time will change by a fraction of 10 to minus 20. And we can see that now. And this is actually a very exciting time. The reason why this is an exciting time is, one is we are continuing to improve this measurement precision. This is the March 2024, this year, we were able to already improve this by another factor of 3. And this is showing you the record we did in 2022, where we can indeed verify general relativity. But the point is not to verify general relativity. The point is really to show that maybe in the near future, every atom, even though they are just a few microns apart, we can tell the time is running differently. Or you can think of this artist who drew the picture called "Time is Soft." What does that mean? Well, it means that there will be a conflict between general relativity, between relativity theory, which means everything is deterministic, and quantum physics, which means there's something in superposition, there's something uncertain. And if you start to measure time over a scale of 1 quantum mechanical wave functions, you're going to see the conflict of quantum physics and general relativity. This is not quantum gravity. Okay, in order to do quantum gravity theory or experiment, you need to go to extremely strong gravitational field. And this is not that. But nevertheless, it will be really quite interesting to get into this physical measurement regime where you can see quantum decoherence is brought together because of the presence of the gravitational potential of the Earth. So we are excited about that and see whether in the future, in the next decade or so, we can improve this by another factor of 10 or 100. At that time, we should start to be able to see when you put atoms in coherent superposition or in entanglement between these different trapping potentials, and you can see their decoherence effects coming in. These are going to be difficult experiments, and then how do you do that? Well, one approach is to do spin entanglement, as I mentioned earlier, to hide away the noise of these lots of particles. And as we all know, these gentlemen won the Nobel Prize because they worked on the spin entanglement on the photon side, the so-called Bell's inequality test early on, to coming from the angle of verifying the foundation of quantum mechanics, and where they showed this weirdness of quantum entanglement does exist. Now we can try to show that atom also have entanglement, of course, and we can use, people are now using this to build quantum computers. We are trying to use this for building better clocks. And so the idea in our particular approach is taking from, for example, pioneers like Vladan Vuletic of MIT. They demonstrated you can put atoms inside a high finesse cavity, and because you have hundreds or thousands of atoms interacting with the same photons inside the cavity, you can actually do the so-called collective measurement, almost like, oh yeah, I'm putting atoms in coherent superposition between spin down and spin up, but my cavity QED field will allow me to spy on whether I'm spin down or spin up. This, remember, was the uncertainty of in principle, I don't know. But when you have thousands of atoms interacting with the same electromagnetic mode of the cavity, you can actually squeeze the noise down because you don't know which atoms interacting with the photon. And so using this approach, we can actually put a sample A inside the cavity, and then after it's being spin squeezed like this, looks like distribution is smaller, we can use this optical lattice like an elevator. We can move sample A out of this place and move sample B inside, and then do spin squeezing also. And after that, we can compare these two spin squeezing the clocks and start to show even at the level of 10 to minus 17 clock precision, spin squeezing is giving us advantage. And the key goal of quantum entanglement or quantum advantage is to show at 10 to minus 20, 10 to minus 21 level, we will be able to use spin entanglement to continue to advance the state of the art. Another way to do it is to scale up the quantum system. Instead of doing a one-dimensional optical lattice, what if we do three-dimensional optical lattice, have three orthogonal beams interfering with each other, creating a three-dimensional crystal, and you can put 1 million atoms in there. If you have a coherence time of 120 seconds, it will allow you to reach a precision of 4 times 10 to minus 20 per second. And this will be amazing. Of course, this also gives rise to a lot of opportunities to study light matter interactions, because atoms, when they are so densely packed, when you put light in there, you have to consider a lot of so-called collective effects. It becomes a quantum simulator where some traditionally condensed matter problems like spin orbital coupling, spin super exchange, SUN symmetries, radiative dipole coupling, when you have one atom with its dipole is connected to the rest of the other reservoirs of atoms. And these are no longer simple linear problems. These are collective many particle physics problems. And you can see the clock turns into a probe to study a lot of a frontier sort of a quantum many body physics problems. And that's also a very exciting frontier. So in order to drive these clocks, one last topic I want to give to you is that, well, we needed to have laser light to have a coherence time to be that long to be able to drive these quantum coherence. And I want to just give you a brief overview of how we control the laser light. You know, this looks like electromagnetic spectrum from radio waves all the way out to X-rays. The visible part of the spectrum is a very narrow sliver here. And if you expand it, this is the laser we use at a 700 nanometer for strontium clock. And we use a typical lasers like that diode laser, which has a spectrum of hundreds of megahertz. Hundreds of megahertz is like zooming in from the visible spectrum by 1 million times. You will have a laser line width of hundreds of megahertz. If you stabilize the laser frequency onto an interferometer, like this very Pro cavity, this was a cavity my thesis advisor, Jan Hall, used to develop a technology that's later on used in LIGO for gravitational wave detection. And so in the early 90s, late 80s, people were already developing technologies that allow you to stabilize lasers to kilohertz scale. And this means you are zooming in another 1 million times for spectral purity. And modern days, we can now squeeze another 1 million times, the third time. And that allows you to reach the laser line width of just a few 10 millihertz or so. And this gives you right now the world's most stable lasers, frequency-wise, that has a tremendously long coherence time. Inverse of this line width is your coherence time, or coherence length. If you use coherence time times the speed of the light, that's the so-called coherence length, meaning if I send a laser beam from Earth to the moon and let it go back and forth, 100 times, you should be able to see microsecond interferometry. And because of the coherence length is so good, even after 100 times of a round trip, you can still see a fringe of interference. Maybe in the next decade or so, we should be able to extend the coherence time to an entire incoherence length of the entire so-called astronomical unit between the Earth and the Sun. And those technology will be tremendously useful, of course, for space satellites, keeping the distance, keeping the communication networks, and so on. But what I want to say is that such technologies will turn into a giant microscope and telescope. It turns into a fundamental physics enabling tool. We can use clocks to directly listen to the gravitational waves. We don't need to build the microsecond interferometer. You can just compare clocks. You can compare clocks to probe dark matter. You can build a clock network around the Earth and build this very long baseline interferometers to probe these fundamental physics phenomena but also has tremendous amount of technological use. You can also use clocks to probe our environment around on the Earth. We talk about weather change, climate change, things are changing on Earth, but because of gravitational potential is connected to the time, the clock, precise clock, will allow you to monitor the ocean level rising and so on. And in order to do this, we also needed actually one more tool, which I haven't told you, that if you have a very stable lasers, as I mentioned earlier in here, but how do you use this to build interferometers, or how do you use this to connect different quantum systems together? We need one more tool, which is actually so-called optical frequency comb. And it's actually a very simple concept. If you have a periodic train of pulses in time, by Fourier transform, you would have in the frequency domain a comb of lines equally spaced. Each one of them is optical frequency, and their absolute distance is guaranteed by the periodicity of the pulse train from the Molelock lasers. And you can actually span a huge electromagnetic spectrum of the entire visible spectrum, for example. And this allows you to build one CW laser, one single CW laser with a very high frequency stability, and connect this to the rest of the electromagnetic spectrum in the visible. It's almost like running a huge reduction gear like this. When one of the laser is keeping track of phase coherence, the rest of the electromagnetic spectrum will keep the same phase because every single tooth in this gear is being attracted for. And for that, Jan Hall and Ted Henschel won the Nobel Prize in 2005. Now we can use such technologies and transmitting signals between, for example, JILA, our laboratory, to NIST, Boulder lab, through these optical frequency combs. In fact, you can transmit signals in air or through the fibers, connecting very, very different systems. In JILA, we have a strontium clock. In NIST Boulder, you have a ytterbium clock, the aluminum trapped ion clocks, and they all can be connected together now, even though they have very, very different wavelength. You can be connected through these optical fibers and through these very stable lasers. And the systems that cannot be compared at 10⁻⁸ level, and start to build these free space network where eventually over tens of kilometer distance, optical clocks can be compared. And if you can do tens of kilometers on Earth, that means you can compare Earth to the satellites as well. One of the reasons why this comparison is useful for fundamental physics is, well, people actually been postulating dark matters are permeating us because there are some mysteries out there that we know from astronomical observations there is dark matter, but so far it's been very elusive. We do not see how dark matter interacts with ordinary matter or ordinary field. One theory is maybe we can find the signature of dark matter by looking for time variations of fundamental constants like fine structure constant alpha. And if you compare clocks of different species, they have a different dependencies on alpha. So by comparing clocks, whether they are drifting and changing in time, maybe will tell you whether this alpha is changing, the fine structure constant alpha is changing, or maybe the electron-proton mass ratio is changing. These are fundamental constants. We don't know if they will always be constant. We do not know if they will be changing. These are just, in some sense, exploratory kind of experiments to try to see whether we can discover something beyond the current framework of physics. And for talking about that, I can't help but mentioning if there's a nuclear clock available, the nuclear clock will allow you to have the sensitivity even much more enhanced by thousands of times, maybe hundreds of thousands of times, because now you're inside the nucleus. You will start to probe sort of a QCD physics and compare with the QED physics that's connecting electrons and photons. So that maybe it's interesting to talk about nuclear clock just a little bit. There's a nuclear structure. Now it's no longer about electrons moving around nucleus. It's directly trying to drive two energy levels inside the nucleus. And that's super exciting if you can use lasers to drive it. Because just like atomic physics went through renaissance in the 1960s when laser was invented, atomic physics was totally different afterwards because everything is not coherent. What if we can do something similar to nuclear physics with lasers to change the nuclear states? If we can do that, you can build a nuclear clock. And in fact, there is one low-lying energy nuclear state that's in so-called isomeric state of thorium-229. And this state lies at the energy scale of 8 eV. So it's something that we can almost access with our laser technologies and has very long lifetime, 10 minutes or so. So this is the nuclei that people have been proposed and been searching for the signal. And in recent years, especially Eka Pike, who has been a pioneer proposing these transitions. And recent years, in fact, this year, their group was the first to show that you can use 10 gigahertz kind of a fluid mixing lasers to drive these nuclear transitions. And so we got excited about that. We thought, well, our group has been building the so-called XUV frequency comb, and we can use this to both act as a laser drive as well as a laser ruler to look at this nuclear transition. So, and this goes to this frequency comb that I just introduced to you earlier. The frequency comb works in the visible spectrum. Can we extend this to the extreme ultraviolet? And turns out it's possible. You heard last year's Nobel Prize went to the so-called attosecond physics. What attosecond physics is doing is they were using very large electrical field generated by highly intense laser beams to ionize make a big perturbation to the Coulomb potential of electrons around nuclei. So then these electrons can be actually coming out of into the continuum and snap back to be recombined to release the energy, and therefore generating very high order harmonics in that process. And you can use to continue to chase down the shorter time scales instead of femtosecond. These pioneers were working on towards attosecond physics. But in our lab, we actually took these two fields together. Very early on in 2005, we started to think about maybe we can, using this attosecond physics generation process of so-called high harmonic generation, and map the frequency comb structure from the visible all the way out to extreme ultraviolet, maybe in the future, even to the X-rays. And the technique we use is to use a build-up cavity. We use a high finesse optical cavity where everything single frequency comb in the visible spectral range is enhanced by the cavity resonance, and it gets enough power to do this attosecond physics kind of work and mapping the frequency comb into extreme ultraviolet. If you're interested, you can follow these references. But this actually now gets really exciting. This dream came true just about a month ago. And we were finally able to generate a frequency comb. Well, we have been able to generate frequency combs for a while from the visible all the way out to the VUV. But for the first time, we can use one of the comb component of the VUV to drive the nuclear transition and measure the absolute frequency of the nuclear transition to the atomic frequency. And this already, the first measurement tells you 12 digits. But what's really most exciting about this is we are finally connecting. I hope this picture gives you some real excitement because you're connecting nuclear physics to atomic physics directly in a phase coherent fashion. And in fact, it's actually really cool to see that we can directly drive the nuclear quadrupole transitions without any hyperfine. When we talk about hyperfine, it's electron interacting with the nuclear spin. This one's just within the nuclei, we can drive directly nuclear quadrupole transitions and actually determine having some real constraints now to the liquid model of the nuclei because the nuclear quadrupole moment tells you the shape of the nuclei. So I want to end my talk to give you this one final thought. Precision measurement is a tool to understand fundamental physics. We know in the 50s when Mossbauer spectroscopy was first invented, and here's the Mossbauer, he was able to study nuclear physics. And in some sense, kilo EV gamma rays can be used to study nuclear structure. When in the experiment done in Harvard by Pond and Rebecca. This is a very famous experiment. That's where the name redshift came from. They were able to use this Mossbauer effect to take a emitter in the basement of Harvard building and let the gamma ray photon go up onto the ceiling, onto the top floor, and it's actually measure when it's absorbed how much energy is being redshifted. And that's how they measured Einstein's general relativity. And remember, when you talk about redshift, you can think about either the photon energy is changing or the clock frequency is different. It's depending on your reference frame, but it's the same equivalent physics model, physics picture. And it's kind of interesting that I mentioned this experiment to you that we did it 2 years ago, that we can use atomic clocks to measure the redshift. Again, the same general relativity effect over just 100 microns. Well, now with a nuclear clock, all these physics can be connected together. And I just think it's really exciting time for quantum science, for atomic physics, and maybe in the soon future for nuclear physics as well. So I want to thank you for that, for your patience and attendance, for listening to my talk. I want to thank my group members who have contributed. Many group members have moved on. But here are the snapshot of people who are currently working on this, for example, strontium-1, the very shallow lattice, strontium-2, the three-dimensional crystals, spin-squeezed clocks, stable lasers with a silicon cavities, collaboration with Jella colleagues, and so on. But finally, I also want to recognize, especially Chong Kun. He was the one who has been in my lab for 7 years, and really really was the one who drove forward on this nuclear clock project, together with new graduate students, Tian and John, as well as a postdoc, Jake. But with that, thank you very much.
Thank you. Yeah, thanks for this fantastic talk. So we really enjoyed this very much. So let's see if there are questions or comments online or in the local room.
Let me turn on my office light. It went off by itself. Okay, I'm back. Yeah, any questions you would like to ask, I'll be happy to respond to.
I think we can ask questions both in Chinese or English.
Yes, in Chinese is fine.
Okay.
Yeah, sorry that I give lecture in English. Sorry about that. It's just because if I give lecture in Chinese, it's going to take twice as long.
I think your English is very good and understandable to our students. We really enjoy that, appreciate that. Yeah. 大家有什么问题没有呢？
我跟你说中文了哈。那个，我请教一下，因为你刚才讲的非常的非常的前沿了。这个我2个比较直接的问题，在你那儿做这个spin entanglement 的那个 optical clock， 这个你估计大概什么时候能够实现？还有就是这个土的这个光中，这个核中，看起来你们也在布局，你估计整个的这个钱，这两个新型的这种钟，大概要多长时间能够最终的实现？你估计
？OK， let's see， 你们还可以看到我的这个 screen 吗？
看到，
可以看到。小军，比方说在这里，这张图上，these are the lines that we see on nuclear transitions, and you can see the line width is on the order.
I don't see the screen anymore.
You cannot see the screen?
No. Probably.
I think you just ended the
sharing.
就是结束了屏幕共享。
对不起，我重新 share 一下。对不起。
Yeah, share it again.
好，现在可以看到了。
Yep, got it.
小军就是刚才我讲，比方说这里有一根线 ，right? This is a spectroscopy line shape. This is actually nuclear transition. at 148 nanometer. And this is the frequency, 2020 terahertz. And we can measure this now with a frequency comb connected to the strontium clock. But the line width, as you can tell, is 100 kilohertz. But when we measure the lifetime, it turns out to be 10 minutes long, meaning when we excite the atom, nuclei, these nuclei are actually embedded in this little crystal that was provided to us by our collaborator, Schumann's group in Vienna, Thorsten Schumann's group from Vienna. And it's kind of amazing. This crystal does not require any laser cooling trapping. It's just sitting there, right, in our vacuum chamber. And we can directly excite these transitions. Very narrow. We don't know how narrow this is going to be, except I can tell you the lifetime is 10 minutes long, the excited state lifetime. And we saw this decay that takes 10 minutes to decay down. And so what it means that this line width is likely limited at the moment by our laser, by our VOV frequency comb. And that's what we are working on to try to improve. We can lock the laser onto these nuclear transitions. And that's already can be running as a clock. But we want to make sure the line width is as narrow as possible. In the future, maybe they will be limited by the crystal physics. There will be some electrical fields. In fact, the splitting here is because of a nuclear quadrupole moment interacting with the electrical field gradient inside the crystal. And so the key question is, how stable do you need the temperature to be for the crystal and so on? And these are just starting, right? This is the very first work 4 weeks ago. And the paper was just written, just submitted. And there's a lot of work to do. And I think the intrinsic quality factor is 10 to the 19th. I think the field will probably take a decade, but it's really super exciting time. Well, we also are thinking about whether we can develop a CW laser at this wavelength to directly drive this nuclear transition. The nuclear transition has two aspects that's interesting. One is the fundamental physics that I mentioned earlier. The other one is more on it's very portable because as I mentioned already, nuclei, the information is hiding inside the nucleus, not in the electrons around the atoms. So they are much more robust against the environmental changes. And so this will be interesting to see whether that's going to be an ultimate portable system, portable clocks. Now, your other question was, you said a spin orbital coupling. Is that what you said? What you said? 小军，
刚才是叶老师问您的，他第一个问题是说就是把那个自旋纠缠起来呀，就利用这个纠缠的体系来做这个进一步提高原子钟的这个精度。叶老师问您，就是想问一下大概什么时候可以实现？您觉得？
对，还有这个土光钟。
Yeah, no, that's great. 我希望叶老师刚才我核光中的问题已经回答了，可以吗？现在回答这个问题。
是，我知道你的这个进展到哪儿。我是只是直接的问的是这个，你估计起来整个这个实现的这个系统实现大概几年之内，或者是一个什么长时间内能够实现？
像比方说这个是 entanglement 就 spin squeezing clock. You're asking about how long this will take, right? So this work has already been published. So this is the work we have already realized. This is the data we took in the lab. So showing spin squeezing is better than classical quantum noise limited clock measurements. But notice that we are showing this only at 10 to minus 17. And you may ask, 为什么没有到10的负20？那是因为要到10的负20需要把它的 coherence 做得很长。我们这里做 spin squeezing 的时候，现在 coherence 做不到很高，因为你把这些 atom entangle 了以后，我们要把它移到腔外面，然后把下面一个组的 atom 再移进来，再做 entanglement。在这个过程当中， technical noise，就是那种 motional noise，还是continue to limit us in terms of how long we can keep the entanglement. And so I think这个工作是我们去年做的，今年发表，现在的工作正在进行的，我们相信现在还没有发表工作，我们可以把这个提高10倍，到就是说能够 spin squeezing 能够在10的负18的地方工作，但是这仍然不能表示 spin squeezing 不是 spin squeezing 的 clock 要好，因为我们不是 spin squeezing 的 clock 已经做到10的负20了，所以真正要说entanglement really is the best， 我们还要继续的努力要把 entanglement 真正做到比所有的原子光中都要好，这我想没有5年到10年可能做不出来。因为我们其他的光中也在往前走，而且现在原子核的光中也出来了，他们也在往前走，所以这是一个 in some sense 就是说这实际上是个很健康的一个competition，并不是说你 spin squeezing 就肯定要被人家好，而是 spin squeezing 提供了一种 inspiration， 就是我们好像觉得 entanglement 马上就要追上来了。我们自己要把不是 entangled 的 system 要做得更好。And right now it's hard to decide which one is better because the strontium clock when I showed you with coherence time of 2 minutes, that clock is going to be able to measure 10 to minus 18 stability at a second. So it's amazing, right? You just take 10 to the 4 seconds to go to 10 to minus 20. And it will be interesting to see how spin squeeze clock can compete in the next 5-10 years.
叶教授，我能问个问题吗？我能问个问题吗？听见吗？
听见。
哦，我那个澳门大学的唐子康，我非常感谢你今天做了一个非常好的一个 talk， 就是有关那个量子计算还有那个原子的光中哦。那我问一个比较特别的问题，我不知道行不行，那你不要介意啊。就是量子计算这一方面，量子计算这方面，就是现在做传统的，就是用entanglement， 就是量子纠缠，这个是必须的条件，就是需要在低温下，当然现在是不断的在变好的。那我从另外一个角度去考虑这个问题的话，比如说经典光学里面的双缝衍射。那2条缝，然后也是看到的是经典光学的结构，那个有亮的，有暗的，有亮的，有暗的，是吧？这个很经典，跟量子好像没什么关系。但我们如果仔细去想的话，比如说我不是用光源去打，用光子一个一个去打，你就会发现打几个光子，比如说10个光子以下，那个光子的分布在屏幕上的分布是非常 random 的，那典型的量子力学的那个测不准原理的乱跑，是吧？
Yes，
那你就几百个打进去也还是这样子，但是你如果几万个、几百万个打进去的话，你就可以看到它的平均值，就有那个那个的 diffraction 那个效果出来了。
Yeah，
你如果2个仔细去比较的话，经典光学的那些一个个的动作跟量子力学初步的那个测不准原理很一样，但最后的结果跟量子力学那个薛定谔方程的那个共轭波函数的平均值也很不一样。我们从这个角度去做了，就是用经典光学为基础的量子计算，我们走了好几步，走了第3步，非常成功了。所以我现在想问一个问题，从经典光学的角度去考虑，跟量子力学的波函数去统一起来，从这个角度去考虑的话，做量子计算，而且跟温度没关系了，就不用考虑这个 entanglement 能不能被温度破坏掉的那个角度。我想问一下，就我说的，从这个角度，你觉得可能性，或者是它的概率性，或者是它的那个原理性，怎么个看法？
您刚才讲的单光子的衍射实验，它 就是说实际上是每个光子自己和自己在进行干涉。你这个可以光子
这个是经典光学上面那个拿来做比较。那我们
It's
现在
okay. 我知道你想说的是什么事情。我想就是说，你说你光子可以干涉，甚至原子也可以这样干涉，分子也可以这样干涉，电子也可以这样干涉，都可以做到。
对
但是你这个工作是每一个光子是和自己在进行干涉，它光子和光子之间没有任何的 entanglement。
对，
所以你是一个 superposition principle
对
it's a quantum mechanical wave function. We all know quantum mechanical wave function itself 和 classical wave function 没有什么区别。It's just a wave function.
但是最后
But
的
the
结果
true
看到
quantum
不是一样的。
mechanics, the true quantum mechanics is actually in the uncertainty principle. In the fact that there's a quadrature of noise. You cannot measure them simultaneously to infinite precision.
Yes.
That's the true quantum mechanics. And so you cannot just say, well, wave function description looks like classical physics, therefore classical physics can represent quantum mechanics. That's actually not true, because when you do entanglement, when you have two photons are entangled, one spin is up, the other one spin also is up. Those are the things you cannot explain with a Young's doublet experiment, because Young's doublet experiment is a single particle physics experiment. As you said, 就像你刚才讲的，你一个光场 random， 你打了多了以后，它就出来一个经典的分布，就像一个 wave function。
对，这个效果上就是很一致的了。就是你开始的时候去看，那是经典那个也表现出量子力学的测不准，然后最后的结果去看经典光学也表现出量子力学的平均值。这个是我们从这里是看，我们是一个去考虑这个问题的一个出发点。但是我们第二步看到了，第三步看到了，好像看上去跟量子力学完全不一样，但是效果上都达到了。所以我问的就是这个问题，就怎么去考虑这个事情。
OK， 我觉得你要去做一下两个 entangled photon 的 interference experiment. That you will be surprised. Do photon counting experiments. These are the experiments people did in the 1970s and 80s. Young's doublet experiments people did it in the 200 years ago. So
但是这个其实也有好几个人家那个有其他轱辘发表过认为了，就是这个经典光学的这个方向去考虑过，但实际上那个光源要非常特别的。已经看到经典光学的那量子纠缠，虽然现在是还不能完全等价就一模一样，但是量子纠缠的这个结果已经是不可否认了。所以这个是怎么个两个连起来？
不可否认，但是不是你说的那个double slit experiment。
那个是就是从那个出发点，我们现在真正现在一步一步往前走的操作方法跟那个是。又借那个概念而已，但是我们用一种非常特殊的光源，但是也是经典的。这个是最好的那个技术问题呢，就是跟温度没有那么敏感。
Sounds good. Maybe you can send me a paper for me to read.
呀，我们可以联系我通过那个冯教授跟你加个微信，到时候跟你聊聊这些事情。
微信我没有，但是你可以发给我 email. That's okay.
发给你没关系，我有你的 email。到时候我跟你沟通。但是这个我觉得是一个非常新的一个方向，新的想法。但是你今天讲的就给我很多启发了。就是这样的话，我要多请教你。
不敢当。
Okay, good. More questions.
Okay, let's see if there are more questions.
谢谢了啊。
老师同学有没有什么问题？
叶老师，我有一个问题。我想问一下您那个土光中的
问的人是谁？
怎么
问的人是谁？
您好，我是北京量子院的博后殷鹏。那我在尤利老师组里，做一元子阵列。我想问一下您的那个土光中的 UV 光源是怎么做的？然后是整个那一套的放土离子的那个晶体。它是放在 cryogenic environment 里面吗？
没有，这个晶体就放在，我们把它 在 room temperature 里面照样可以看到，不需要放在 cryogenic environment 里面。
那就是室温的热生子，它会导致线宽的展宽有多少？
现在这个问题很好，这个问题现在我们还不能向你解释，因为我们现在可以把它 cool 到另外一个 temperature， 可以看到它的线会移动，但是我们的这个线宽有可能是因为我们的 VUV comb line is still too broad. We are still thinking about this, and you can already see there's a different line width here. So probably there's some interesting physics already because of these different nuclear moments. And so they are acting on electrical field gradient of the crystal. And you can actually see they have manifested as different line widths. So it's not completely limited by our laser line width, but I think the narrowest line is what we are going to investigate first to see how much our laser line width is contributing. 您说的就是说以后要去看线宽有多少是为生质造成的。This is going to take some time to investigate, and this will be actually exciting time for the entire field to study things like this, like material science. You can have different doping, you can have different crystals, and so on. But right now, the crystal is calcium fluoride, and it's actually can be cooled down, as is shown here, calcium fluoride with the thorium doping. It can be cooled down to 140 Kelvin, or it can be just sitting in room temperature. We can see those nuclear transitions. So 你另外一个问题是我们是怎么样产生这个光源的，对吗？
是的。
Yeah, so it's a femtosecond laser in fiber laser at 1040 nanometer. We lock that laser onto a build-up cavity. Just like as shown here in the bottom left, this frequency comb red is 1040 nanometer. And we lock onto the cavity where each frequency comb component is enhanced by a cavity resonance. So inside this cavity, you can have actually this frequency comb being vastly enhanced. Instead of 100 watt, it becomes 10 kilowatt of average power. And that means every pulse is strong enough to reach this intensity of 10 to the 13 watts per centimeter square to allow you to do non-perturbative harmonic generation of so-called high harmonic generation for the attosecond physics. And in that attosecond generation, because we're doing this at a very high repetition frequency, this is a very high rep rate, 100 megahertz repetition frequency. We can now having a real frequency comb structure underneath those high harmonic generation features. That's how we use this, mapping the frequency comb from the infrared to the VUV.
OK. 还有一个问题就是您刚刚说您的重频是100兆，就这个重频对您这个转化效率是什么影响？就是重频越低，导致单个脉冲的能量越高，它效率越高，还是说这个重频要控制在一定范围？
If 你的这个重复频率就是 repetition frequency, if it's too low, in the traditional attosecond physics, people do those work like the people like Ferencz Cross and so on. Typically the repetition rate is kilohertz or sometimes early days in hertz. These you wouldn't be able to keep track of a laser phase, so you do not have a frequency comb. So you have to have high repetition rate to generate a frequency comb. And so we were able to produce a frequency comb first in the visible, and then you try to do frequency comb. When you have a frequency comb in the visible, how do you generate attosecond physics? Because the pulse is coming very, very fast. Every 10 nanoseconds, there's a pulse, but usually that pulse is too doesn't have enough intensity to ionize the sample or do non-perturbative harmonic generation. So that's why we use cavities to enhance the power. Does that make sense?
理解了，谢谢你。
Okay.
Okay, I think there's a question locally here, so.
Thank you, Professor Ye, for your nice talk. I'm Wong Sang-Wu from Hainan University. My question is, as the molecular clock has some advantages compared to the atomic clock and compared to the nuclear clock? Thank you.
Yeah, molecular clock. I think in the early days, molecular clock was very interesting because the molecules have lots of transitions. So you can allow you to build frequency standards over very different spectral regions, vibrational transition, rotational transition. Right now, at this age, I think the molecular clock is not as competitive, partly because the frequency cone technology allow you to go anywhere you want to go within the visible spectrum, and also to mid-infrared to infrared. So you don't really necessarily, if you have a frequency standard in one location, say at a strontium, just for talking, you can certainly derive very precise electromagnetic radiations in the mid-IR. So you don't really need molecular clock there to give you a frequency standard anymore. You may say, well, the molecular clock can give you different flavors of fundamental physics probe. That's certainly true. Your molecular clock is based on the vibrational transitions or rotational transitions. You're looking at sort of a motional states of nuclei in the harmonic potential that's created by the electrons around the nuclei. And you're looking at potentially some interesting physics of how nuclei attract each other, maybe even small scale gravitational force between the nuclei, but that would be very model heavy. You have to do a lot of theory models to kind of tease any physics out of it. But I personally don't think, in some sense, molecular clock, some homonuclear molecules, for example, you can go to some vibrationally excited state and will live there for a long time, just because they do not have a dipole moment, so they are not being excited by black body radiations and so on. But in order to achieve very long, because the molecular frequency tends to be lower, and in order to achieve very long quality factors, you have to have very, very long coherence time, and that puts demand on the technology. So anyway, it's another interesting quantum system platform. You can use molecules to explore really interesting physics, like a search for possible electron-electrical dipole moment with molecules, but not necessarily as a clock, is what I'm trying to say.
I think maybe I'm wrong. The last limitation for the precision of the atomic clock or molecular clock is the lifetime of the energy state. So I think the molecular system can have more long lifetime state. Is that right? Compared to the atomic system.
That's correct. The problem is that long lifetime is not enough. You have to, for example, which system right now demonstrated the highest coherence time? It's atomic system. It's a quantum state engineering. So long lifetime is good. Suppose you have a quantum system that has a lifetime of 1 kilosecond versus a system that has only 100 seconds. 1 kilosecond is better. However, if the transition frequency is also lower by a factor of 10, then that advantage goes away, because fundamentally it's how many oscillations you have, the so-called quality factor. So if in molecular system, because the oscillations at the terahertz or tens of terahertz kind of a frequency, your coherence time would have to be much longer than the atomic system to be competitive. And oftentimes the coherence time is not just limited by the lifetime, but limited by other things like perturbations of your background, by the vibration of your optical lattice. And so you have to make sure all the other technical contributions are gone.
Thank you.
Yeah.
I have a question. May I ask?
Sure, please.
Yeah. I may be the only nuclear theorist in this group here. And since you mentioned about nuclear physics, I'm very excited about the discussion. One of the things about nuclear structure is that we learn a whole host of collective motions that nuclei has. It could be vibrational, it can be rotational, and there are also some symmetries of a specific type that people have seen. But the energy level, of course, is quite often in the tens, if not MeV levels. And so presumably the physics is quite different from the atomic clock or even the molecular clock. Would the collective motions of nuclei have any impact on making a nuclear clock, for example?
Yeah, Dr. Heng, they're exactly right. In some sense, the nuclear physics is totally different from atomic physics. It will be very different. And
yes.
if you look at this picture here, this is actually the picture I showed earlier, but I did not emphasize too much. You can see those red dots are atomic transition, optical atomic transitions.
Mm-hmm.
Those blue dots are nuclear transition. And you're right, if you look at the nuclear energies, they are all in the 10 keV to...
Yeah, at least.
These are all the nuclear transitions that eventually, if we have gamma rays that can be coherently generated,
that's right, then
the nuclear physics will be completely new revolution. But
right.
Today, what we can do is this little one, thorium, down here, down here. And that's the only reason is because I can generate coherent laser light to address this nuclear transition. That's why I'm doing this. But maybe in the future, maybe we can do also uranium.
Yeah.
This one is just below 100 EV.
That's right.
It's actually possible to do this one. And,
right.
and you start to and these are two examples of nuclear physics that you can potentially be accessible within the next decade in order to get a coherent gamma rays to do overall nuclear physics. That I dare not to predict how long that would take. Maybe we need to find ways to coherently seed these free electron lasers and all that. Yeah, it requires a new technology to be developed.
Good, thank you.
So there's a question from the student. So,
叶老师您好，感谢您的演讲。我是海南大学的一个本科生，然后我好奇的一点是，您刚讲的那些钟对 GPS 会有影响，它具体会有什么样的一个作用呢？谢谢。
钟对什么基本什么的影响
？GPS， 您刚提到 GPS 嘛，包括我们国家的那个北斗，对。
你想问什么？就是对 GPS 有什么影响？
您那些钟对这些 GPS 会有一些什么具体的作用吗
？OK， 像对 GPS 来讲的话，你比方说，如果你要用光钟来做 GPS， 当然可以，但是光钟呢，它的精度很高，所以 GPS 现在是靠 microwave 来传信号。这个 microwave 的信号传播不能够满足这些光钟的精度，就是说，如果你光钟来做 GPS 的话，实际上有点大材小用，除非你把光钟的就组成一张网以后，你的飞机或者你的卫星和这个钟进行联系的时候，是直接用光来传播，这就可以 take advantage of 光钟的精度。所以我想，一般来说 GPS 如果用 microwave technology， 你再提高10倍，我觉得 GPS 在地球上的应用已经是足够。但是如果你说要以后做星际旅行，以后要到 Mars， 要到其他更远的星球去的话，你的 GPS 的那种精度就不够，就要用光钟这样的钟才能够来帮你做下一步的navigation system。这是一个。另外一个，光钟你把它联系起来以后，你可以来测一些，比方说GPS 现在测不到的，比方说 continental 之间的 drift，mountain 之间的变化。GPS 是一种，就是说今天我把你定一下位置，不是说能够把测量到 很微弱的那种变化，在地球上面的变化。我不知道这个有没有回答你的问题。还有一个我要讲一下，就是说 GPS 有时候会关掉，人家把 GPS 关掉了，你的飞机怎么飞呢？但是如果你在飞机上自己有这样的钟，你 GPS 就是关掉了，你可以自己导航。这是其中也是一个很重要的一个应用。就是如果你自己有一个陀螺，你自己有一台钟，你自己或者有一台magnetic sensor， 你自己可以导航。比方说你20分钟以内，你可以从point A to point B。If you know what time it is, you can control your trajectory. So even without GPS, you can still guide yourself. And that sometimes is actually very, very interesting application.
好，谢谢老师。
最后一个问题吧。Last question.
So any more questions? I see that.
Last one.
没有了。
I saw that Xibo was Xibo is also here. You see, maybe Xibo would like to say something because Professor Junye just mentioned some work from him. He is also online here.
Okay, great.
Xibo 你在吗？
金龙我在。
哎。
不好意思，我早上听一半，然后学生突
谢
然
谢叶老师精彩的报告。就是我的问题是，也是看到这个河中非常兴奋，这也是第一次看到，就是说这个河中它除了寿命方面的优势，就是10 minutes 以外，它现在除了激光之外，最大的那个 systematic error 在哪里啊？就是说除了光学，它有没有像 atomic interaction 这样的就是 fatal systematic？
Yeah, that's an interesting question. That I'm sure there will be some collective effects we can study. When you have lots of particles together, even if it's a nuclei, and you have a photon that's connecting them, I'm sure there will be some really interesting many-body physics involving nuclear physics in there. But that's not something we can see at the moment. What would be interesting is to narrow the line width down to start to see line shape that's fundamentally limited by the environment. Say in this case, it's a crystal. People are also thinking about you can trap these thorium in ion form, in trapped ion, and so on. So there will be a lot of interesting work that's going to take place, and you can study, for example, in the crystal. I'm sure you will see some environmental limitations of the crystal. The crystal itself generating electrical field. The crystal itself generates electrical field gradient that will interact with the nuclear quadrupole to give you the line splitting I mentioned earlier. And so if the laser line width gets narrower and the laser power gets higher, then what I want to do is to do quantum optics with nuclear physics, where you can generate pi/2 pulses. You can start to think about building nuclear qubit, doing Ramsey spectroscopy, doing Ramsey fringe experiments. That would be, all these things are just completely new. So the road is wide open for us to explore. You can do spin echoes. You can do a lot of things to understand what environment is going to limit this. And as we know from atomic physics over the past 40 years, whenever we see a limitation, we take that as an opportunity to understand some new physics, and then we remove that limitation altogether, and we go on to the next step. I have no doubt this will be the same.
Thank you.